Welcome all. I am B. JAMUNA, Assistant Professor, ECE Department. In this lecture, I am going to explain about Introduction to 8086 Microprocessor. So, first we are going to discuss about what is microprocessor. So, microprocessor is the brain of microcomputer. So, it is a single chip which is capable of processing the data. So what operation the microprocessor is to perform means it is used to fetch, decode, and execute some instructions. And it is going to execute set of instructions. So coming to the internal architecture of the microprocessor, that will be somewhat complex. So now we'll discuss the 8086 microprocessor. So before going to the 8086 microprocessor, so we are going to have the evolutions of microprocessors are there. So it is going to start from the 4-bit microprocessor. So 4-bit microprocessor means this all will be depends upon the ALU operations. So 4-bit ALU operations it can perform at a time. It is called as a 4-bit operation. In the same way, it is going to perform the 8-bit and 16-bit. Like that, we are going to have an evolutions of microprocessors are there. So in this 4-bit, first here we are going to discuss the 8-bit microprocessor. So the IC number for 8-bit microprocessor is an 8085 microprocessor. So the 8086 is the 16-bit microprocessor. So now you'll see the features of 8086 microprocessor. So the 8086 microprocessor is a 16-bit microprocessor, and it is going to manufactured with respect to the HMAS technology. And coming to the address bus, 8086 has a 20-bit address bus, means it can access up to 2^20 memory locations. So the memory of 8086 processor is 1 megabyte, and it is going to have a multiplexed address as well as the data bus. So total it is going to have the 60 AD0 to AD15 address and data multiplexed. And as well as the address lines are from A16 to 19. So the total address lines are the 20 address lines and the data lines are the 16. So the multiplexed address and the data lines are AD0 to AD15 or the multiplexed data and address lines. And it is going to provide 14 16-bit registers. It consisting of 14 16-bit registers. And it is going to operate in 2 different types of modes of operations. That is minimum mode as well as the maximum mode of operation. Coming to the minimum mode means it is going to use only the single processor. And in the maximum mode, it is going to use the multi-processor. And coming to, it can prefetches up to the 6 instructions bytes from memory and queues, and in order to speed up the instruction execution. And 8086 processor can support up to 64K input-output ports. Coming to the power supply, it requires the plus 5 volts of power supply. And coming to the IC, it is in the form of dual inline package, and it is going to consisting of 40-pin IC. So these all are the features of 8086 microprocessor. 8086 is a 16-bit microprocessor, and it is going to perform the memory. It is in the form of 1 MB of memory. So coming to the internal architecture of 8086 microprocessor. So this is the internal architecture of 8086 microprocessor. Internal architecture can be divided into 2 parts. That is bus interface unit, and next one is the execution unit. So the bus interface unit, it is going to fetch us the instructions, and the execution unit will take the instructions from the bus interface unit, and again it can give it to given the instruction. It is giving and taking process. It is going to perform in a execution unit. And bus interface unit, it is going to perform the fetch type of instruction, fetches and particular instruction. And how many operations it is going to perform is the bus interface unit. It is going to fetch the instruction to the memory from data or memory. It is going to fetch an instruction, and it is going to write the data to the memory, and it is going to write the data from the memory, and read the data from the memory. And coming to the functional parts, so how these operations can be performed by using an 80 bus interface unit means by using an functional parts, that is instruction pointer and segment register and instruction byte queue. Instruction pointer, segment register, instruction byte queue. So these all are the functional parts of a bus interface unit. By using these functional parts, it is going to perform, it is going to perform the operation. What operations it is going to perform? It is going to fetch the instructions to data from memory. So that operation it is going to perform by using these three functional parts. So coming to the instruction pointer, it is going to indicate with the IP. It is going to execute the next instruction to be fetched. And segment register, it is going to 8086 consisting of 4 segment registers that are code segment, data segment, stack segment, and extra segment. So each segment consisting of 16-bit registers. And the next is instruction byte queue. So instruction byte queue consisting of the 6 bytes, and it is going to execute in the form of first in first out basis. So this operation it is going to perform by using an bus interface unit. And coming to the execution unit, so what execution unit will perform is it is going to perform the operation in the form of taking and giving policy it is going to perform. And it is going to, whatever the instructions come from the bus interface unit, it is bus interface unit will fetch the instructions. Now it is going to decode the particular instructions. After decoding, it is going to execute the instructions. So the execution unit contains the control circuitry. Means it is going to control the total circuitry by using various internal operations. Coming to the functional parts of the execution unit consisting of an general purpose registers, that is GPRS, pointer registers, pointer and index registers, and ALU, flag registers, and timing and control unit. So it is going to totally, it consisting of the 5 different parts, 5 different functional parts. Bus interface unit consisting of 3 functional parts, and the execution unit consisting of the 5 functional parts. So what are the 5 functional parts means? The first one is the general purpose registers. So what are general purpose registers? AX, BX, CX, and DX are the general purpose register. So AX indicates that accumulator register, BX is the base register, CX is the counter register, and DX is data register. So these all registers are in the form of 16-bit register. So each 16-bit register, again, it can be divided into the 2 8-bit of registers, so that it can be divided in the form of AH and AL. So AX can be divided into AH and AL. So AH is the higher order byte and AL is the lower order byte. So each byte consisting of an 8 bits of data. So like that, each 16-bit register can be divided into the two 8-bit registers in the form of higher order as well as the lower order. So lower order is indicated with 0 to 7, total 8 bits, and the higher order is 8 to 15. So total 16-bit. In the same way, BX register is also divided into the BH and BL, and the CX register is CH and CL, that is the counter register. And the data register DX is divided into DH and DL. So this is the first part, and the next is the pointer registers as well as the index registers. So the pointer registers and index registers are also in the form of 16-bit register. So the pointer registers are stack pointer, base pointer, and coming to the index registers, source index register as well as the destination index register. And coming to the next part, it is going to consisting of ALU, arithmetic and logic unit. It is going to perform all arithmetical and the logical operations. So after performing that particular operation, the output is connected to the flag. That is, the flag is also called as an output status register. So in this ALU is a 16-bit register. So here it is going to perform all arithmetical and the logical operations. And next it can be given to the flag register. So the flag register of 8086 is consisting of an 16-bit flag register. So in that, whatever the outputs we are going to get from the ALU, so it is going to set that which type of flag is it is going to set. So that operation it is going to perform. And coming to the next functional part, that is decoding unit. It is going to perform the decode the instructions, and after decoding, it is going to given to the timing and control circuit. It is going to control that particular instructions. So this operation it is going to perform. So the 8086 architecture is divided into the two parts. It is going to, that is bus interface unit and the execution unit. So the main aim of the processor 8086 processor is used to perform fetch the instructions, decode the instruction, and execute the instructions. So by using the bus interface unit, it is going to fetch the instruction. So for the bus interface unit, from where it is going to get the input means that can be decided by the execution unit. So execution unit will give an input. That input will take from the bus interface unit, and it is going to fetch that particular instruction, and again it is going to given to the execution unit, and execution unit will execute the particular instructions. So this operation it is going to perform. So now we will see each and every part briefly. So it is going to consisting of the two blocks, that is bus interface unit and the execution unit. So bus interface unit contains instruction queue, segment register, instruction pointer, and the address adder. And coming to the control circuitry of the execution unit, it is going to consisting of an instruction decoder, ALU, pointer and the index register, and the flag register. So what bus interface unit will perform? Bus interface unit performs all bus operations, means such as instruction fetching, reading and writing operands for memory, and calculating the addresses of the memory operands. All these operations will performed by the bus interface unit. And execution unit executes instructions from the instruction fetch by byte in the form of queue. So this operation it is going to perform. So now we'll see the instruction queue. So why we are using the instruction queue means to increase the execution speed. To increase the execution speed, we can go for the instruction queue. So bus interface unit fetch as many as 6 instruction bytes. Instruction queue consisting of 6 instruction bytes from the time from the memory. So total it is going to consisting of 6 instruction bytes. So all 6 bytes are arranged in first out structure. So the 6-byte register it is called as an instruction queue. So the instructions from the queue are taken sequentially for performing the decoding operation. So this prefetching operation of bus interface unit may be in parallel with execution operation of execution unit. So it is going to improve the speed execution of the instruction. So while opcode is fetched by the bus interface unit, the execution unit previously decoded instruction concurrently. So thus means bus interface unit along with the execution unit forms a pipeline operation. So how the pipelining operation it is going to perform is, it is going to perform the operation bus interface unit along with the execution unit. Like that, it is going to perform the operation of pipelining operation. So now you can see the physical address formation. How we are going to give the physical address formation? So here I'm going to explain with the example. So here physical address equal to the 10H into segment address plus the offset address. So here I am going to consider the segment address equal to 1005H and offset address equal to 5555H. So here, this is in the form of hexadecimal number. So now we are going to perform in the form of binary representation, the segment address 1005. So 1 is represented as in the form of 0001 and 0 is 0000 and again 00000 and 5 is represented in the form of 0101. So it is going to shifted by 4-bit positions, means it is going to perform the 10H operation. So just you are going to shift the 4-bit positions. So 0001 will shift in the form of left side operation. In the right, we are going to put as it is 0000. So the 1005 is shifted to the left bit position. So we are going to mention in the last position, it is going to replace with the 0000. So it is going to added with respect to the offset address. So what is the offset address? Offset address equal to 5555H. So you are going to indicate with 5 means 0, 1, 0, 1. So you are going to add 0, 1, 0, 1, 0, 1, 0, 1. So 1005, that is the 4-bit shifted bits can be added to the 5555. Then what you are going to get? The physical address equal to 0001, 0101, 0101, 1010, and 0101. So 155 and 1010 is represented as an A, and again 0101 equal to 5. So the physical address equal to 155A5. So like that, we are going to calculate the physical address. So physical address equal to 4-bit shift left shift bit positions. That is, or simply we can take it as 10H into segment address plus offset address. So like that, we are going to indicate. And this is about the bus interface unit. It is going to perform. And coming to the execution unit, it has a 16-bit ALU. 16-bit ALU means it is able to perform all arithmetic and the logical operations. So after performing the ALU operation, it is going to reflect the results to the flag register. So the output can be given to the flag register. So the 16-bit flag register reflects the results of execution by ALU. So next, the decoding unit is there, no? The decoding unit decodes the opcode bytes. And the timing and control unit derives the necessary control signals, and it is going to execute the instructions. So this operation will perform the execution unit. And the functional part of the execution unit is, it is going to consisting of the registers. Register organization. So in the 8086, in the bus interface unit, we have seen that in the execution unit, we have seen that it is going to consisting of the general purpose registers and segment registers, as well as the pointer and the index registers. So this all together, we can call it as a register organization. So this can be represented as a register organization of 8086 microprocessor. So in that, the first, it is going to consisting of the general purpose registers or a general data registers. The 8086 consisting of the 4 general purpose registers, that is AX, BX, CX, and the DX registers. So the AX is the accumulator register. This is the 16-bit register. These 16-bit registers can be divided into the 2 8-bit registers, that is AH and AL. That will be indicate that the 2 8-bit register. And the next is the base register and counter register, and the last one is the data register. So these all are the general purpose or data registers. Coming to the segment registers, it is going to consisting of 8086 is going to consisting of 4 segment registers. That is the core segment, stack segment, data segment, and extra segment. So these segment registers are also in the form of 16-bit register. It is going to hold the particular data. Segment registers are used for holding the data. So code segment register is used to hold code type of data. Stack segment register is used to hold stack type of data. And data segment register, it is used to hold data type of data segment type of data. And extra data can be stored in an extra segment. And the next one is, it is going to, in the registers, we are going to have a flags or PSW. PSW, it is called as a program status word, or simply it is called as a flag. Coming to the flag register of 8086, it is going to have a 16-bit flag register. So it is going to give the status to the ALU operation. Whatever the ALU operations it is going to perform, further it is going to give the status. The result of ALU can be given to the flag, and the particular flag will give the status. Means it is going to consisting of total 9 different flags. No, either the 0 flag will set or parity flag will set. That will be depends upon the ALU operations. And coming to the next type of registers, that is the pointers and the index registers. So the pointer and index registers. So these all are in the form of 16-bit registers. It is going to have stack pointer and the base pointer. And coming to the index registers, it is going to have source index register, destination index register, and one more 16-bit register is the instruction pointer. So these all registers comes under the register organization of 8086 microprocessor. So how many? It is going to consisting of totally 14 16-bit registers. 14 16-bit registers, it is going to consist in a 8086 microprocessor. So that simply we can divide into the general purpose registers, segment registers, pointers, and index registers. Next. So in detail, we can see all these types of registers. So first, general purpose register. So in the general purpose register, as I already told that we are going to have a 4 different types of general purpose registers are there. So the first one is the AX register, that is called as the accumulator register. It can be used to perform the 16-bit accumulation operations. So with the lower 8 bits of AX is designated as an AL, and the higher 8 bits acts as AH. So the total 16-bit register, it can be divided into the 2 parts, that is AH and AL. So lower 8 bits is indicated with the AL, and the higher 8 bits is indicated with the AH. And coming to the BX register, it can be called as a base register. It is used as an offset storage for forming the physical address. So if you want to form the physical address, what we have done, that is the base address plus the offset address. No? So in that case, we can use the BX register. Coming to the CX register, by default, the CX register can be used as a counter register. So this register can be used in the case of the string and the loop instructions. And coming to the DX register, DX is used as a data register, as an implicit operand or the destination register. In case of few instructions, it is going to use. So in case of few instructions means it is used to hold the data for multiplying and the division operations. In that case, we can use this particular type of register. So these all are the general purpose registers. Coming to the segment registers, it is going to have 4 different types of segment registers are there. That is code segment, data segment, stack segment, and extra segment. So coming to the code segment, the CS register, it is used for addressing a memory location in the code segment of the memory. So in the code segment, the executable program is stored. So whatever we are going to execute the particular program, that can be stored in the code segment. So coming to the data segment, the register used for the data segment is the DS register. So it is going to use for addressing the data segment of the memory. So where we are going to have that particular data. So it is going to indicate the particular address of the particular memory. So or where the data is stored. And the next is the stack segment. The stack segment register is used for addressing the stack segment of the memory. So that is the memory which is used to store the stack type of data. And extra segment is the additional data segment. This is also used for addressing the extra segment of the memory. So where the particular data is stored. So these all type of registers can be used to hold the data, either in the form of code type or data or stack type, as well as the extra type of data. So like that, it is going to store. And the next type of registers are the pointers and the index registers. So the pointers and index registers are stores offset address within the particular segments. It is used to store the offset address. So where here we are going to have a pointer registers are instruction pointer, base pointer, and the stack pointer. So in the instruction pointer, it is going to store the offset address in the code segment. If you want to store the offset address in the code segment, we can use the instruction pointer. And if you want to store the offset address in data segment, we can use the base pointer. And if you want to store offset address of stack segment, then we can use the stack pointer. So these pointer registers are used to store offset address within the particular segment. And coming to the index registers, it is going to have 2 types of index register, that is source index register and the destination index register. So coming to the source index register, it is used for storing the offset address of the source data. Whatever the offset address we are going to have further source data in data segment. So that for storing that particular offset address of the source data, then we can use the source index register. and it is also used for indexed or base indexed and register indirect addressing modes. So we are going to have the different types of addressing modes for the 8086. No? So in all these addressing modes, like indexed addressing mode, based index addressing mode, register addressing mode, and register indirect addressing modes, we can use the source index register. Coming to the destination index, it is used for storing offset address of the destination data or extra segment. So it can also be used for the indexed as well as based index and the register indexed addressing mode. So like this, the register available in a 8086 microprocessor. And coming to the flag register, the flag register of 8086 consisting of total 16-bit flag register. So it is going to start from 0 to 15, and it is going to have conditional flags as well as the control flags. So coming to the conditional flags, it is going to consisting of 5 different types of conditional flags. So the first one is the carry flag, that is CY. Next, PF is the parity flag, AC is the auxiliary carry flag, and ZF is the zero flag, and SF is the sign flag, and OF is the overflow flag. So these all are the conditional flags. And coming to the control flags, it is going to consisting of 3 different types of control flags are there. One is DF, that is the directional flag, TF trap flag, IF is the interrupt flag. So like that, it is going to consisting of 6 conditional flags and 3 are the control flags. So it is going to, it is going to consisting of a 16-bit register. So coming to the carry flag, after performing the ALU operations, if it is going to get a carry, then the particular flag will be set. So for that purpose, we can use the carry flag. And coming to the parity flag, so in this, we are going to have the 2 different types of parities, that is even parity and odd parity. So after performing the arithmetical operations, so in the result, we can check that the number of ones will be even, then the even parity will set. So number of ones will be odd, then the odd parity will be set. Like that, it is going to have set that particular flag. And the next type of flag is auxiliary carry. So whenever the carry generate from the second bit to the third bit, then that particular time, the particular flag will set. Zero flag means, so when the result after performing the ALU operations, when the result we are going to get equal to 0, then at time the particular flag will be set, that is the zero flag. And sign flag, it is going to indicate that either the result is in the form of positive or the negative. And overflow means if you are going to perform the 4-bit operations, ALU operations, then the result will be more than the 8 bits, 4 bits, then the particular time the zero flag will be set. So like that, it is going to consisting of the, these all can be used for the conditional flags. So what are the conditional flags? Carry flag, parity flag, auxiliary carry flag, zero flag, and the sign flag. So these same type of flags can be available in a 8085. But it is going to compatible with the 8086, except overflow flag is not there in a 8085. So coming to the control flag, it is going to have trap flag, interrupt flag, and the direction flag. So this is the flag register organization of 8086. So the same thing, it is going to have status or conditional code flags means sign flag. Sign flag is set when the result of operation is negative. So when the result after performing the ALU operations, when the result is negative, then the particular flag will be set. Same zero flag. When the result of operation is 0, then that particular flag will be set. Auxiliary carry flag means it is going to set when there is a carry from lower nibble or lower 4 bits of the operation. If we are going to get the carry from lower nibble or the lower 4 bits of the operation, then the particular flag will be set. Coming to the parity flag, so if the particular flag is set, in the result, if it is going to consisting of even number of ones in the lower byte. So carry flag is set when there is a carry from the result. And the same thing, overflow flag is set when the result of signed operations overflows then the particular flag will be set. So these all comes under the conditional code flags or the status flags. So now the control flags. The control flag is the first is the trap flag. So when the trap flag is set means when trap flag is set means the process enters into a single step execution mode. Means it is going to execute the program instruction by instruction. So it is going to execute in the form of single step. So after executing the one instruction, it is going to execute the another instruction. So like that operation it is going to perform means in that case the trap flag will set. And coming to the interrupt flag. So it is an interrupt enable or the disable flag. So if it is set means the maskable interrupts are organized by the processor. Otherwise, this type of flag will be ignored. So next lecture we'll discuss about the interrupts of 8086. In that we can see that whether the interrupt is enabled or disabled. In that particular case, then the interrupt flag will be used. And coming to the direction flag, the direction flag is used in the string operations. So if it is set means string bytes are accessed from the higher memory address to the lower memory address. Means higher to the lower means it is in the form of auto decrement mode. In that particular case, the direction flag will set from lower memory address to the higher memory address, or it is in the form of auto incrementing mode. So the direction flag is used to operate in the form of string operations. So in the string operations are accessed from higher memory address to the lower memory address. Higher to lower means it is in the form of auto decrement mode, or it is in the form of lower to the higher, then it is called as an auto incrementing mode. So auto incrementing mode means the particular flag will be in the form of preset. And auto decrementing mode means the directional flag is in the form of set. So like that, it is going to perform the operation. So it is going to control the ALU operations by using these particular type of control flags. So this is about the flag. This is about the register organization of 8086. So now we'll discuss the memory segmentation of 8086. So as I already told that what is the memory of 8086 processor? 8086 processor consisting of 1 MB of physical memory. Those are the size of address bus of 8086 is 20. Address bus equal to 20 and the data bus equal to 16. So it is going to have 20 address bits means, and it is able to perform the 1 megabyte of physical memory operations. So 2 power 20 means it is going to perform 1 megabyte. So the complete 1 megabyte of memory can be divided into the 16 segments. Coming to the memory segmentation, it is the memory is divided into the parts, means it is in the form of segments. So how many segments? It is divided into the 16 segments. So each segment is consisting of 64 kilobyte size. So and 64 kilobyte size, and it is addressed by one of the segment register. And the address of the segment, how we are going to assign the address of the segment means it is going to assign as 0000H to F000H respectively. Like that, we are going to assign the address of the segment. So the offset address is used to address a specific memory location within the segment register. So the offset values are from 0000H to F000H. So that the physical address range from, so the total physical address range from 5 bits, that is 00000H to FFFFH. So like that, it is going to have a segmentation. So the memory segmentation, it is going to have the memory of 1 MB of memory. So the total 1 MB of memory can be divided into the 16 segments. So each of 64 kilobyte size, and it is going to address by the one of the segment registers. So in the segment registers, in the physical memory organization, it is going to have, it is in the form of overlapping segment as well as a non-overlapping segment. So it is going to have segment 1 and the segment 2 is there, no? So this is in the form of non-overlapping. So each segment separately, it is going to consisting of the 64 kilobytes of memory, and it is going to have a space. So it is not in the form of overlapping. So this type of segmentation is called as a non-overlapping segmentation. So this is the overlapping segmentation. So you can observe the CS1 offset IP1, this is, and this is CS2 offset IP2, that is the segment 2. So the segment 2 is overlapped with the segment 1. So this 64 kilobytes and this will be the 64 kilobytes. So this is segment 1 and this is the segment 2. So like that, it is going to overlap the particular address. So this type of addressing is called as an overlapping segments. So coming to the advantages, it is going to allow the memory capacity of the 1 MB and it is going to actual address, it is going to handled by the 16-bit size and allows the placing of the code, data, stack portions of the same program in different parts of the memory for its protection. So these are the advantages of memory segmentation. Coming to the pin configuration of 8086, it is going to consisting of total 40 pin IC and it is in the form of dual inline package. So DIP package, dual inline package, just observe the pin configuration of 8086. So as I already told that the 8086 can be operated in the form of two different modes of operation, that is minimum mode as well as the maximum mode. And for the minimum mode, it is going to some pins can be performed the different operations and other than that, it can be performed in the form of maximum mode. So this totally consisting of 40 pin IC and it is going to require the 5 volts of power supply and whatever we discussed, it is going to have the address and the data multiplex lines are there, no? That is from AD0 to AD15 and it is going to have an address and the status lines are there, that is A16 to A19 and this total operation can be performed by using an MN by MX bar signal. So if MN by MX bar equal to 0, the processor can be operated in the maximum mode. If MN by MX bar equal to 1, then the processor is operated in the form of minimum mode. And these all are the signals, read and write signals. So like that, this is the pin configuration of 8086. So now we can see the clear description of each and every pin. So first it is going to consisting of the address and data pins, that is in the form of AD15 to AD0. So these are the multiplexed memory IO address and data lines. So that is address remains on the line during the T1 state. In the T1 state, the address will be remains and in the while the data is available in the data bus. That is in the form of T2, T3 and this in the right state, TW and the T4. So address will be remains on the T1 state and the data is available on the remaining state, that is T2, T3, TW and the T4. So when the memory or IO device is not able to respond quickly during the transfer, that is in the form of wait states, TW is called as a wait states. It is going to insert it between the T3 and T4. So if we are by disabling the ready input of the 8086. So if it is not able to respond quickly, then it is going to wait in a TW state. So the bus activity during the wait state is same as the during the T3. And coming to the address lines, that is A16, A17, A18, A19. These all are the multiplexed address and the status lines. So the status lines are S3, S4, S5 and the S6 are the status lines. So the S4 and S3, it is going to indicate which segment register is presently used for the memory access. So S4 and S3, the two status registers, no, it is going to perform the 4 different operations, 0, 0, 0, 1, 1, 0 and the 1, 1. So if it is 0, 0 means it is going to perform the alternate data operation, 0, 1 means stack type of operation, 1, 0 means code or none type of operation, 1, 1 means data. So the status of interrupt enabled flag bit is updated at the beginning of each clock cycle and it is going to display on the S5. So the status line S6 is always low. So in the status register, the overall operation is based on the 2 different types of the status register, that is S3 and S4. Based on S3 and S4, it is going to indicate that it is going to give the alternate type of data or stack type of or code or data type of data. So these are the status lines. And coming to the next pin, that is the BHE, bus high enable, or the status line S7. So the bus high enable is used to indicate the transfer of data over the higher order. Bus high enable, higher order data. So the total data lines are D0 to D16. In that higher order data means it is going to indicate D8 to D15 on the data bus. So whenever the BHE bar is low during the T1 for the read operation, and write the interrupt acknowledgement cycle. So whenever the byte is to be transferred on higher byte of data bus. So the BHE bar and the A0, these two signals is indicates which byte of data is to be transferred. So by the combination of BHE and A0, it is going to indicate that, means if it is 00 means it is going to transfer the whole word. If it is 01 means it is going to transfer upper byte from or to or. Then 10 means upper byte from or to even address, even word, and 11 means it is going to transfer none of the word. So like that it is going to transfer. And RD bar signal is the read signal. So this is the active low signal. It indicates that the processor is performing memory or the read operation, that is IO read operation. And the next ready signal, this is the acknowledgement from the slow device or the memory, and it is going to have completed data transfer. And the next type of signal is the INTR, that is interrupt request. So this is the level triggered input. This is sampled during the last clock cycle of the each instruction to be determine the availability of the request. And test bar. So this input is examined by the wait instruction. So whenever the test pin goes low means execution will continue. So or else the processor remains in the wait state. So this is the clock input signal. It is going to provide, the clock means it is going to provide basic timing for the processor operation, and it is in the form of square wave. This NMI is the non-maskable interrupt signal, and the reset means it is going to cause the process to terminate the present activity. Then we can go for the reset. And the main is MN by MX bar signal. If it equal to 1 means it is going to operate in the minimum mode, and if it is 0 means it is going to operate in the maximum mode. So when the minimum mode operation is selected means the 8086 provides all control signals needed to implement the memory and IO interface. So M by IO bar, a memory as well as the input output. If M by IO bar signal equal to 1 means it is going to perform the memory operation. If it is 0 means it is going to perform the IO operation. INTA is the interrupt acknowledgement. Means whenever it goes low means when the processor is accepted the interrupt. That can be as given by the interrupt acknowledgement signal. And DT by R bar signal is the data transmit as well as the receive signal. Whenever it equal to 1 means when the processor is to transmit the data. If it is 0 means it is going to receive the data. So these all are the pins available on the 8086 processor. Okay, thank you.